Alright, let's take a look at the first example problem in Chapter 6. We've done a couple a little bit more complicated, but this one's not to be looked over, or not to be not taken seriously. It's a good problem. They give us that a force is applied on this block that is sitting on a horizontal surface, and there is friction. They give us the static coefficient and the kinetic coefficient of friction, and the mass. Oh, sorry. And they give us the magnitude of the force. And they want to know, given this information about the friction and the mass, does it slide when we apply this force? And then, what is the magnitude of the frictional force? Okay, well, does it slide? That means, is the acceleration non-zero? Is it zero or is it not? If it's not zero, that means it's sliding. So let's take a look, see what we can do. If it helps, first of all, you could draw this force as a force like this with the angle of 30 degrees becoming like that. So let's go ahead and make a free body diagram and do just that. Here's my horizontal, 30 degrees below, we have our applied force. And let's go ahead and break it up real quick. We have some component in the x direction and some component in the y direction. Now, what else we got on there? We always have mg going down and a normal force perpendicular to the plane that it's resting on. And they told us that there is friction. So if motion were to occur, it would occur from this force, and some magnitude of it is pointing to the right. Therefore, friction is going to act in the opposite direction, to the left. Okay, now we got our free body diagram. They want to know, does it slide? Well, I only see two forces in the x direction. I see this one, and I see this one. So is the acceleration going to be equal to 0? Well, we can say what conditions make it 0. What conditions give an acceleration equal to 0? Well, that would be saying that the x component of this frictional force is equal but opposite to the maximum frictional force that could occur. And that's why they gave us the static coefficient of friction. So we can figure out what that maximum frictional force is. So let's find that. Draw my angle theta there real quick. The maximum frictional force. Actually, let's just go ahead and break this into a component. We can get a number for the x component that we're measuring it against. So the f of x, component-wise, would be f cosine and then of theta, and we have a 12 Newton force. And it'd be the cosine. In this case, I would put in a negative 30 degrees. And you'll still get a positive answer back. But this is a 10.39 Newton force. That's how much is attempting to move the block to the right. So let's hold on to that. And then to calculate the frictional force, we need to look in, well, let's just write it out. What's the frictional force? It's equal to mu times the normal force. So that normal force part right there means that we got to do Newton's second law in the y direction. Okay, doing this gives us a normal force going up right here. We have a minus mg going down and some component of force f sub y, and I'm just going to go ahead and replace that with plus f sine, and this would be equal to f sine of that theta. And this is where you really need to put in the negative 30 degrees, because that negative will end up giving us the actual downward force, a negative force, and that's what we need. It is not coming off the surface, so there is no acceleration in the normal direction or in the y direction. So we can say that the normal force is equal to, rearranging this gives me an mg minus an f sine of minus 30. Alright, we can plug in our frictional force now, and let's use the mu sub s. So the frictional force max would be using the static coefficient, and then we can throw this term that we just found in here, mg minus f sine of negative 30 degrees. And what we get is a much larger force, 59.08 newtons. And we can compare these two. The maximum frictional force that can possibly occur is a 59 Newton force, but we're only applying 10 in the x direction. So does it move? No. The acceleration is indeed 0 in this case. And when would it start moving? As soon as the applied force, so let's say we just started pushing harder and harder and harder, but at the same angle, as soon as this got to where it was, the x component was greater than that maximum force of friction, it'll start to move. And then it'll actually accelerate for a little bit unless you let off and then balance the force. Because remember, the force of static friction is always going to be bigger than the force of kinetic friction. So right when you break that barrier, you apply a horizontal force of 59.09 maybe, right? 59.09 is just slightly bigger than, it's going to break free, it's going to accelerate for a little bit. Most of our problems are going to just ask when it breaks free, or they're going to just consider kinetic friction all by itself. It'll already be in motion type of thing. So there's our answer, no. But that's not how much friction is being applied, right? We did a quiz on this, and a lot of people just calculated the maximum frictional force. Well, this is why I'm redoing this problem. The amount of friction is actually equal to that number right there. It balances itself until it gets bigger than this number right here, and then it would start moving. So we can prove that too, though. If we look in the x direction, free body diagram, we have this force and this force. So we have some force in the x direction, that's from our applied force, minus the force of friction, and that equals some mass times acceleration. Now we just found out that the acceleration is equal to 0. So cross that out and we find out that the frictional force is equal to f of x, or f cosine theta, or 12 newtons times the cosine of negative 30 degrees. And so the frictional force ends up equaling that 10.39 newtons. Common sense kind of can get us to that final answer also, just knowing that it's gonna push back just as hard as the friction will push back just as hard as we push until friction can't overcome us anymore. As soon as we get to that breaking point, which in this case was a little over 59 newtons, once you push more than that, it will start to move. So in this case, we weren't pushing hard enough. No, it did not accelerate. No, it did not move. And we can prove what the frictional force was at that moment.